SuDS is a drainage technique for urban development that mimics natural drainage and does not adversely affect the aquatic environment. By mimicking natural drainage, SuDS aim to reduce surface water flooding, improve water quality, and enhance the amenity and biodiversity of the environment. With conventional asphalt or concrete paving systems, rainwater runoff rapidly enters the drainage system. Conventional drainage systems can be quickly overwhelmed, and this can lead to downstream flooding. With a sustainable urban drainage system such as a permeable pavement, the surface water is temporarily stored and gradually released into the ground or directed to the next stage of the SuDS management train. In this case, the peak flow rate is delayed and the volume of water is slowly released, helping to reduce the risk of flooding. In this new high-density housing project, the existing drainage system could not cope with any additional runoff from the proposed development. Therefore, the local authority required a SuDS system with no discharge of surface water from the development. To satisfy the local authority requirements, permeable paving was the only feasible option for the roads and driveways. SuDS mimics natural drainage by lowering flow rates, increasing water storage capacity, and reducing the transport of pollution to the water environment. Traditional drainage systems allow harmful pollutants to be flushed directly into the drainage system. Sustainable urban drainage systems act like a filter, trapping and reducing the transportation of pollutants. The leading body in SuDS research is the Construction Industry Research and Information Association. They found that up to 95% of suspended solids and up to 90% of hydrocarbons can be removed by permeable pavements. To help design cost-effective permeable pavements, Brett Landscaping and Building Products have developed PermCalc, free online software that works to the British Standard methodology with a user-friendly interface. PermCalc determines the various types and thickness of pavement layers and calculates the cost of the road or car park using default or user-defined values. This estimation facility extends to costing other adjacent impermeable paved areas, curbs and drain connectors. This ability to compare different approaches makes PermCalc particularly valuable and saves time when determining a cost-effective project solution. Permeable pavement systems fall into three categories. System A allows for total filtration. In this case, all water passes between the blocks and infiltrates through the pavement layers and into the subgrade. Some temporary water retention occurs in the permeable subbase layer, allowing for initial storage before reaching the subgrade. In situations where the existing subgrade may not be capable of absorbing all the water, System B includes outlet pipes connected to the permeable subbase. The outlets are designed to facilitate gradual drainage to sewers or watercourses. Where the existing subgrade has low permeability or other environmental factors that may have adverse effects, infiltration may not be a viable option. System C incorporates a flexible, impermeable membrane, effectively forming a storage tank beneath the pavement layers. Often, permeable pavements are installed on sloping sites. To prevent water collecting at the lowest point and reducing storage capacity, it is possible to create separate permeable pavements by using a terrace system. In the case of roads, internal dams can be installed which restrict the flow of water within the pavement. Placing services within a permeable pavement should be avoided if possible, but if this is unavoidable, it may be necessary to construct an impermeable service trench within the permeable pavement. Let's take a look at the overall construction process. First, excavate down to subgrade level and compact the subgrade. The subgrade or capping should be trimmed to provide a nominal fall away from building structures. For System A, trim the subgrade to provide nominal falls away from structures. For System B, trim the subgrade to provide a nominal fall to the outlet positions and away from structures. And for System C, trim the capping to provide a nominal fall to the outlet positions. Where full or partial infiltration systems are used, it is recommended that a geotextile is installed between the subbase and subgrade to prevent migration of fines into the subbase. In the case of all System C pavements, a capping layer is required which should be trimmed to provide a nominal fall to the outfall positions. The thickness of the capping will vary depending on the condition of the subgrade, the site drainage, water table levels and recent weather conditions. System C pavements include an impermeable membrane which contains all water entering into the pavement. To avoid damage to the membrane when installing System C pavements, it may be necessary to provide a smooth surface by either blinding the capping with fine aggregate or installing a geotextile. The aggregate used for the subbase is described as 4 to 20 coarse graded aggregate. The aggregate must have particular properties. It must have a void ratio of at least 30% to provide water storage, and the stone size should fall between 4 and 20 mm. In addition, the stone must be angular, allowing a greater interlock and produced from hard, durable rock to withstand high point loading. Depending on the design, the coarse graded aggregate should be laid in 100 to 150 mm layers and compacted using a medium-sized roller with little or no vibration. The coarse graded aggregate is self-compacting to a degree, and excessive compacting may crush the individual particles or reduce the voids ratio. To cope with higher volumes of traffic, the design will require the installation of a layer of hydraulically bound coarse graded aggregate. This aggregate is similar to coarse graded aggregate but includes a nominal amount of cement to increase the stiffness. This is installed in the same manner as coarse graded aggregate. It is important to ensure that the pavement is protected from the elements while the hydraulically bound coarse graded aggregate sets. Other than the plant and equipment required to build the pavements, no traffic should be allowed onto the pavement until it is completed. However, if there is a need to use roads and hard-standing areas as temporary routes during the construction phase of the project, temporary access can be provided by laying a dense bitumen macadam layer. If the DBM layer is to be laid over the coarse graded aggregate, then a tracked paver machine must be used because a wheeled paver could cause damage and become stuck in the coarse graded aggregate. The DBM can substitute the hydraulically bound coarse graded aggregate layer, but because water cannot be stored in the DBM layer, the designer will need to check that there is still sufficient storage in the pavement and may have to increase the depth of the coarse graded aggregate to compensate. Prior to installing the permeable blocks, the DBM is punched or cored with 75 mm diameter holes on a 750 mm grid to allow the water to flow into the underlaying pavement layers. The holes are then cleared of debris and filled with either coarse graded aggregate or bedding aggregate. The 50 mm thick bedding layer is a durable free draining aggregate with a maximum particle size of 6 mm. This is sufficiently coarse to allow the flow of water, yet fine enough to permit the accurate installation of the paving blocks. Suitable aggregate can be supplied in 25 kg or bulk bags. First, the bedding layer is placed and levelled and the screed rails are set in place. Prior to screeding, the bedding layer is pre-compacted, forcing the bedding layer aggregate into the sub-base aggregate, thus minimising long-term settlement. Screeding of the bedding layer can be done manually or mechanically. The level of the bedding layer is screeded relative to edge restraints such as curbs. The screed rails are then removed and the depressions left by screed rails are carefully reinstated. Brett Landscaping and Building Products produce blocks suitable for permeable pavements in a range of types and colours. Some types of blocks can be supplied for machine laying, but they are usually laid by hand in a herringbone pattern. When laying blocks in this way, you may need to make cuts to complete the paving surface. Use a manual block cutter to cut these blocks. The blocks are then set into the bedding layer with a suitable plate compactor. Prior to compacting, be sure to remove any debris and sweep the area clean. At this point, the pavement is inspected for the correct joint spaces, alignment and lipping. Any defects are corrected before the joint aggregate is applied. Once checks and corrections have been completed, the joint aggregate is spread and swept into the joints. The aggregate used is the same as the bedding aggregate. Using a plate compactor, the aggregate is then compacted into the joints. During this process, it will be necessary to top up the joints with additional aggregate and recompact. A final inspection is carried out and where necessary, corrections are made. All that remains is to sweep the surface clean and hand the site over to the client.